Hello world, it's me. The other day I was looking through this old interface age. I was looking for something for one of my Intel boards, and I came across this picture of this single board computer, and I said, hey, I got one of those things. So I dug it out, and sure enough, it's the same board that's in this picture. It's a Miller Technology M-80, and this magazine article is in November of 1980. The copyright on the board is actually 1979, but this particular board was made in week 44 of 1980. So that's about the right time for this. And you look at this board, and it's a single board computer, and I have a soft spot in my heart for single board computers of that age so I thought, well, let me dig this thing out, and maybe there's somebody else out there that has one of these things. The problem with this is I haven't been able to find any documentation on this. There's a couple of these little articles that specify it kind of as a new product thing, but in terms of a schematic or information on the monitor or whatever else was available on this, I just haven't been able to get any information at all. So, who knows how many of these actually were made, how popular they were, but they did show up in these magazines for a couple of years. So if we look at this, it's a Z80 machine. So what we've got is we have 2K of EPROM, of ROM here, and we have 2K of static RAM. We have this is the INS8154. It's got two 8-bit ports and let's see, 128 bytes of RAM, so it's 1 kilobit of RAM. And then you can see that this is a 2 megahertz crystal, a little CMOS inverter here, probably for the crystal, and then I would guess these are decoding. And one of the nice things about this board is it's got a lot of nice silk screening on it. This tells us that the address here is 0, that's 400, this is 1000 and 1400, and you can see all of these over here are decoded address in like 1K blocks. So it should be a fairly simple board to reverse engineer. Particularly, what we're going to do off from the very beginning is we're going to presume that this board is working when it was shut down or when it was taken out, and we're going to presume that all this silk screen is right, and that's a big presumption, but it's a good place to start. When I have a board like this, I'll go kind of a combination of routes, and in one case I would completely go through and do a test on the board and find out where every connection is, and that would be if I had a long-term interest in this board, or if I knew that there were people that were dying for a full-blown schematic of this board, additional information, I would go through and find everything about it. This is going to be more in the lines of what I'm going to do is find out just what I need to know about the board, and then I'm going to start popping some software in here. And what I really want to do is I want to find out how this thing communicates. If we look at this article in the interface age, it says that it has a serial port. It says both the monitor and it had the Wang Tiny Basic. So both the monitor and this basic use a serial I/O for communication. So this obviously doesn't have any teletype drivers on it. This is the original monitor. The label had come off, but I had a photograph of this board, so I recreated the label for this. And so this is the monitor. It says 300 baud. So obviously I think they were either thinking of teletype or RS-232. So let's presume that it was RS-232, and my guess is, since there's no RS-232 drivers on this, they were actually doing a 5-volt interface, and really the only thing that they could have been coming out would be a finger on this 8154 I/O. So what I want to do first is get this board up and going and find out how to send things out this 8154. Now this video is probably going to skip around a bit because a lot of that would be fairly boring, but some of the techniques that I use, I just wanted to share to show you how I go about reverse engineering a board like this. So the first task I want to do is I want to find out how this I/O is decoded. We can see that we have the addresses for all of the memory, but we don't know anything about how that's decoded or how we communicate with that guy. So I am going to do a little bit of probing around on this board to see how this is deselected and how it's wired to the Z80, and so that I can communicate with this guy. Then after I do that, I'll write a little bit of test code to slowly bring up and figure out if this Z80 is working properly, or if there's actually something wrong with this board. When I go about reverse engineering something like this, the first thing I want to do is document this. So I'm going to take photographs of it. I'm going to go through and look to see if there's anything unusual. If if this had more than the 24 pin sockets, I would make sure that they were bottom justified like you would think. There is one thing here that's kind of funny. This is a 14 pin device in a 16 pin socket. So I need to see if there's actually pins there, or if this could be more than one device. So that's a little bit goofy. This doesn't have any jumpers on it. If it did have jumpers, I would document where all the jumpers are, but this is really a simple board. There just isn't much going on this, so it should be fairly straightforward to reverse engineer it. But the first thing I want to do is document this to make sure that if I need to, I can go back to where I am now and I don't cause a problem that could have easily been prevented. Okay, so let me document it and I'll be back. All right, so I got some nice photographs of it. I took some notes about it, but like I said, there just isn't a lot on this. The next thing I want to do is I'm going to remove the components that are hard to replace or impossible to replace, like this monitor. I want to make sure that I don't do anything that's going to screw up that monitor, presuming that it's okay. There could be a lot of bit rot in that, but we're going to presume the monitor's okay. I'll take the monitor chip out and see if I can download that. I'm also going to take out this 8154 and the Z80. The 8154 particularly because it's a bit of a pricey chip. The Z80, I have others, but I'm going to go ahead and take that out because when I'm doing testing on this, just with my ohm meter here, I don't want to have a bunch of raking marks along the side of all the pins. It's kind of sad when you look at a beautiful board and it's got little marks on it where, it's been probed to death on all of these. So I'm going to take out the I/O chip, the Z80, and the monitor. I'm not too worried about the RAMs, and I'm not worried about any of this decoding stuff because I've got those aplenty. Okay, so let me go ahead and pop those things out. We'll go on from there. All right, I took out the components that I was really worried about, and you can see here I have data sheets I've printed out for all of the chips that are on this. So as I go through and probe things, I can, save some time by looking at the data sheets. So what I want to know first is, as I mentioned, how is this I/O chip being decoded? So in other words, how do I talk to this? What port address am I using and so forth in order to talk to this I/O chip? So if we look at the pin configuration for this I/O, there's a number of pins here that we're interested in. So we're interested in, this is the write. So actually it's the not write. This is the not read. This is a reset, not reset. And then there's CS0, which is inverted, CS1, which is not inverted, and the memory or I/O selection. All of these are addresses, so we can see that it has address 0 through 6. Okay, so it's only got 7 bits of address. It doesn't need to use the 8th bit of address. There's just not enough in this to need the 8th bit of addressing. There's an interrupt request, and then there is the port A, port B. So these are all, these are the ports there, and then this is the data byte there. Okay, so this is data, port, port, port. So these are the ones that we're interested in: the write, the read, the reset, and the two chip selects. CS0 is active low and CS1 is active high, and then the memory I/O. If we know how all of this is decoded on this board, then we'll be able to talk to that guy. So unfortunately, these sockets don't have a good place to probe, so I'm just putting in another little socket that is going to be easier to probe. Okay, so I've doubled those up. Now let's find out where these go. So the Z80 is nice in that the read and write can be used directly to select, to read and write into a memory chip. They don't have to be buffered or timed with anything else. So let's check to make sure that these all just go through to the Z80. So on this one, we're looking at the write, which is 38, 40, 39, 38. And on the Z80, that should be 21 or 22. Okay, so that's there. The read is 21 on the Z80 and the next one down. Okay, so the read and write go straight through. So the write on this one is straight through to the Z80 pin 22. The read goes straight through to the Z80 pin 21. Okay, that's how we expected that. Next one down is the restart. The restart on this one is 36, 40, 39, 38, 37, 36. Okay, so 36 on that, and on the Z80 it's 26. 1, 22, 23, 24, 25, 26. 21, 22, 23, 24, 25, 26. 40, 39, 38, 37, 36. There's nothing there. So let's go hunting around for that restart. Now, it is possible that's coming in from the bus. And when I'm checking these, you can see I'm sliding this probe around, but I use the back of the probe here. So I'm using the little curved part. I'm making sure that I don't scratch this up. If I really cared, if this were something like out of my Altair, what I would use would be a little piece of solder wick. Take a little piece of solder wick, grab it with this, and then I would actually use the solder wick to make sure that I wouldn't scratch anything. So that's how I would go around and check things to make sure that. Oh, there it is. Okay, so it comes out to that reset is J4. So that reset is J4. So are these in? No, they're not. So these look like there's actually jumpers across there, but those, like there's a trace back across there, but these are actually not jumpered. These are open. So that's connected to J4. Is this other side then connected to the Z80? The Z80 is 26, 21, 22, 23, 24, 25, 26. Okay, so that's a bit worrying that these are not connected together. So that reset comes out to J4. The reset on the Z80 comes out to J4 on the left, and this is J4 on the right. So this has me a little bit more worried about these other ones because none of these are connected. I probed those. Okay, so that's something to keep in mind. We want to find out where the rest of those go to see if those need to be jumpered or not. Because that reset, in order to reset this guy from the same thing that's resetting the processor, that jumper has to be installed. So that's already the first question. Is J4 okay, not jumpered? So we'll have to work on that and figure that out. Okay, so let's look at the chip select 0. Chip select 0 on this guy is 35, 40, 39, 38, 37, 36, 40, 39, 38, 37, 36, 35. Okay, so is that chip select coming from this 74 LS154? So in other words, is it being used, this decoder? Okay, well that's kind of funny. I kind of thought it would be in that decoder. What about this? This is a 7432, so this is a quad 2 input OR. Somebody's got to be decoding that. Okay, so there we go. So he is in 8, 9. He's on 9 of the 74134. What's the, or that's 7432, I mean. 7432, 9 is a input. 7432, so on a 7432, 9 is the input. It's gate 3 input. So that means he's coming from somewhere else too. That he might be connected to that. So he's on the 7432, which is U10. U10 9. I'm going to write in here U10 is the 7432 in case I read that wrong. So that's on U9, so he's going to somewhere else. So let's find out where else is going to. 40, 39, 38, 37, 36, 35. Okay, so he's on that. He wasn't on this, he wasn't on that. He's probably not on that inverter. Okay, let's see if he's on. There he is. So 20, 19. So he's on the Z80, which is U2. That's on U2 19. U2 19 is the memory request. Memory request low. Memory request. So that's interesting. That means that this is using, well, no, maybe that's just for the memory. No, because, I don't think we know yet. Let's look where CS1 is. CS1 is 34, 40, 39, 38, 37, 36, 35, 34. Let's do the same thing. See if he's on that decoder. He's not on that decoder. Is he in that OR gate? Okay, so he's 8, 9, 10 on that OR gate. So he goes to U10, 10. That OR gate 10 is the other input to that OR gate. Okay, so that means that he's coming from somewhere else. He's not coming out of that OR gate. He's coming from somewhere else, and the other place he's coming from is probably the Z80. One, two, three, 4. Pin 4, so he's coming out of U2, pin 4, which is A14. Okay, so for this guy to be selected, A14 has to equal 1. CS0, the memory request, has to be low. So M request has to equal 0. So that means that this is apparently only memory mapped. So that means the I/O in this is not accessed using input and output instructions. The I/O in this has to be memory mapped, and so you input and output to the ports as a memory address rather than as a port address, because there's no other way this would be enabled other than when memory request goes low. So we'll know a little bit more when we find out where that guy's going, but so this is interesting. The first thing that we know for sure now is that this is memory mapped and not I/O mapped, the I/O in this. Okay, and let's look at this last one, 33. 21, 22, 23. $33. Do the same thing. Is he on? Well, actually, he's not going to. Well, I don't think he's on a decoder. I don't think at this point that he would be decoded with the rest of these. No, I guess he could be. He's not. Okay, let's find him on the Z80 then. Oop, that was easy. 40, 39, 38, 37. Okay, so this is U237. U237 is A7. Okay, so if A7 is equal to 0, we're talking to the I/O. If A7 is equal to 1, we're talking to the memory. Okay, so just to check, there's nothing else that we need to know about this guy. Those are ports. The interrupt, so let's see where that interrupt, if that's where that's going. 21, 22, 23, 24, 25. So that's interrupt. He comes out to a pad right there. Yep, so he's connected to a pad right there. He may just be going off board or something. Yeah, so that interrupt is not connected. So he just comes out to the test point. Okay, so I need to look at this. I think we have all the information now on how that's decoded, but while we've got everything set up, let's find the voltages on this. Okay, so to find the voltages, what do we know that this has to have? It's going to have, well, it's got a 2708 EPROM, so that means it's going to have 5, minus 5, and 12. Where are those? Here they are. Okay, so of 2708, okay, so the 2708 has ground on here, so this is the ground. Pin 24 is the plus 5. Pin 21 is the minus 5. And pin 19 is the 12. Okay, so we know this board has to have 5, minus 5, and 12. The 2114s don't take anything else. The Z80, of course, is only 5 volts. That was its big advantage over the 8080, was it was only a 5 volt device. These are all 5 volts. They could be using something more for that crystal, but probably just 5 volts. And this guy, his data sheet, he is just 5 volts. Okay, so let's find those on the finger, the pinout. Okay, so pin 24 first. Okay, we got a good connection. That's our 5 volt. Okay, so that's this big one right here that says 5 volts. So 1, 2, 3, 4, 5, 6. So that's on 6. The next one that we're interested in is the minus 5, 24, 23, 22, 21. The minus 5 is E, A, B, C, D, E. It's marked right there. That's on E. The minus 12 is on 19. Minus 12, let's find that. I thought I got it here. No. Oh, it's right there. 1, 2, 3, 4, 5. So that's on pin 5. And the ground is this one here marked to ground. See, ground is 12. There's ground. Okay, so ground is 10, 11, 12, 13. And then probably also the same pin on the back. Yep, because you can see that, this is the alphabet row, this is the letter row, they're connected together. So this is also on the back. So that guy there on the back, remember on this 2x22 pin, this is a standard vector type of thing, and these are all lettered on the back, numbered on the front, but there's some letters missing. There's O and Q and O and Q and I are missing on this. So this one on the back is actually that would be, it's not going to be Q. Q is missing. Elemental P. It must be P. That's P because Q, and that's R and S. So that must be P. So 13 and P. Okay. I think. I'll put a question mark by that. All right. So now we know the power on this. We know the decoding on that. And the only question that I have, I do want to find out where these other jumpers go because I am worried that they're not actually jumpered. So let's find out where these jumpers go. So J11, J11 J11 doesn't seem to be going anywhere. Oh, my meter turned off. I hate it when that happens. J11. There he is. 20, 19, 18, 17, 16. So J11 goes to U216, which is the interrupt. Okay, so that makes sense. He's just not connected. You could wire him to anything you wanted. That's a J11 on the left side, J12 on the left side, J13 on the left side. J12, 20, 21, 22, 23. J12 is 23, which is the bus acknowledge. U223. Okay. J3 on the left-hand side. 21, 22, 23, 24, 25. It's 25. Did I count that last one right? This is the bus request. Let me go back to that last one. J12, I said that he went to 22, 21, 22, 23. That was actually 24. J12L goes to U224. I think I knew I counted wrong, which is the weight. Okay, so those are important ones. The weight and the bus request both should be connected to something. They shouldn't just be floating. Let's look to see what they are on this other side. So this other side, J11, okay, those are all 11, 12, and 13 are connected together. So J11, 12, and 13 on the right-hand side are all connected together, and my guess is that they're connected to ground or 5 volts. So those are all plus 5. So I think there needs to be a jumper across those or a pull-up because otherwise if weight falls low, this processor will go into a wait state. If the bus request fell low, this processor would go into a wait state and everything would tri-state. And if an interrupt came in, this would constantly be servicing an interrupt. So I need to look up to see if the Z80, I don't remember on the Z80, if it has pull-up resistors on those three and those don't need to be connected, or if those should be connected to something, if there should be a resistor across those three. So that's something we got to keep in mind. If this doesn't fire up, maybe those need to be either jumpered to 5 volts or have a pull-up. So that's a little bit worrisome that maybe this board has never been run before. If those need to be there and they're not there, but we'll worry about that when we get there. All right, we know the voltages now. We know how this guy's accessed, how he's decoded. He's memory mapped, and we can figure out where the addresses are, and I'll look at that here in a second. And the only thing that's we don't know is about those jumpers. All right, so when I am going to use this, I'm not going to solder to any of these fingers. I mean, this thing here, this has been around for 40 years and nobody soldered to these fingers. I'm not going to do that. So I have a bunch of these 2x22 connectors. In fact, these were ones that I bought or had. These are wire wrapped ones. I thought I was going to use these on my mill mod system because, the mill mod system, this board is exactly the same size as that. This is the mill mod EPROM memory board, and see, it's the same as this. This is the same finger, same size, same board. This was a standard board back then, and so I have these connectors left over. So what I'm going to do is I'm going to make sure that I don't jerry-rig this. I want to have a nice elegant solution because you're just looking for trouble. If you either solder to these things directly or you use clips or whatever, it's just looking for trouble. So I'm actually going to make up a power connector for this so I can plug it in and have good reliable power and know that's not going to be one of my problems. Let me go ahead and make a connector for that. And while I have this in my hands, let me look at this and check that pin out. The opposite of 13, so this is the back of this. The opposite of 13 is indeed P. Remember, so I wasn't sure which one we're actually missing, but it was the opposite of 13 is P. So on the back of that, the power is the ground, is pin 13, and the opposite side is P. Okay, so let me go ahead and make that connector, and then we'll be back. All right, I made my connector, put little labels on it, and check it one more time. Okay, so I think that's good. I'm going to turn my power supply on, and let's hope that nothing smokes. Okay, I have my voltages pretty low on this. The currents are all really low. The currents are essentially 0 on all of these. A little bit on the 5 volt. Okay, so I'm going to let this, I'm not worried. There's no electrolytics on this. I'm not worried about reforming anything, but I'm going to let this just sit for a little while we look at that address question again. Of how where that guy is decoded. So let's work our way through that. So if we look at the things that were important, were A14, the memory request line, and then this is our 8154. Okay, so if we look at A14 or 8154, so we know that for this to be enabled, A14 had to be 1, and the memory request had to be 0. So this is 1, 0, and that will enable this. And then if we look at A7, so I guess let me do it this way. We'll put A7 here, so A7 0 and A7 1. If A7 is 0, this is enabled and it is I/O. If A7 is 1, A14 is 1, this is enabled and this is a memory. So what that means, A14, this means that at 0x4000 through 0x407F, because that's when this is still 0, this is all I/O. And then at 0x4080 through 0x40FF, this is all memory. Okay, because this A7 is the most significant bit in that digit. So that most significant bit in that digit, if it's 0, meaning that it's 0 through 7, then this is 0 and we're talking to I/O. If that most significant bit goes up and so this digit is 8 or anything above 8, then we're talking to the memory. And then this 4, this loops around. So, this memory is overlapped. This would be enabled if this is 0x4 or if it's 0x5 or 6 or 7. And then it would be disabled for 8, 14, 15, so 15, 14, 13, 12. So this needs to be a 1. So it would be disabled at, it'd be enabled at 4, 5, 6, 7, but it would be disabled at 8. Okay, so it wouldn't be enabled at 8, 9, A or B, but at C, which is 1100, D, E, F. I'm sorry. So I can talk to this chip right here at 4000, 5, 6, 7, C, D, E, or F. So those are all overlapped. But there's no use, unless it's really convenient, unless you're doing a relative jump or something, there's no reason you would talk to those. But it's good to keep that in mind, that because the Z80 you can do relative jumps. And you can jump forward or you can jump back up to 125 or 128 or something like that. These might be useful for a relative jump, but I guess I don't see that. So I'm not sure why we would use. So I'm not sure if we'll ever use anything other than just the 4. Okay, so long story short is 4000 to 407F, I'm talking to the I/O registers in this, because this chip, if we look at it, it's got a bunch of registers that we write to. But instead of those being I/O mapped, they're memory mapped. So we talk to those registers just using memory commands. We want to talk to the memory, we go from 4080 to 40FF. And those will be our 128 bytes of memory in there. Right, because from 80 to FF is 128 bytes. So there's 128 bytes of RAM, and then I don't think there's 128 bytes of registers, but they're probably doing more just selected bits, so they're not using all 128 of those registers in the I/O. Okay, this all looks good. Nobody is hot yet. The RAM's not hot. One other thing I want to check while I'm... Oh, I guess I don't need to. This is static RAM, so I don't need to see how they're refreshing that. If they're using the refresh on this Z80, because this is static RAM, it doesn't use that refresh. So I don't need to check to see what that refresh is doing in that, because that refresh isn't going to affect these, and that refresh certainly wouldn't be affecting that guy. All right, so what I'm going to do now is let this go ahead and burn in. I'll take it up to its full 5 volts. Just let it set for a while. Make sure nobody gets hot, and then I will plug these two guys back in and start writing some code and putting an EPROM in. Next time we'll look at this clock, make sure we've got a good clock signal going into the Z80. It's critical. And then we'll go on and start writing some software and seeing if we can get some bits to go out this port. Okay, well that's enough for this video. I appreciate you watching, and if you have any questions, let me know. Talk to you later. Bye-bye.